Alright, so this is a little weird because the lesson's separate from the example problems, but I did want to go over the example problems with a board. So I have the example problems right here. The information will be there, and then like the problem will be there. I'm not going to exactly follow the way they do it, mostly because if you guys know, I always do the problem just a little bit different. Two reasons. One, I do it the way that makes sense to me. And two, having two different versions of the same problem coming at you, you get to pick which one makes the most sense to you. So let's go and look at this first example of Boyle's law. It says a sample of helium gas is compressed from 4 liters to 2.5 liters at a constant temperature. If the pressure of the gas in the 4-liter volume is at 210 kilopascals, what will the pressure be at 2.5 liters? So let's just, you don't have to draw the pictures, but let's say this is the 4-liter container and it's being squished down to 2.5. So just going off of the stuff we know, if this is at 210 kilopascals, we know that this should probably be higher because you're squeezing it, so the pressure is going to be higher. So let's go ahead and look. We're using Boyle's law for this. That's the example problem is Boyle's law. So that's P1V1 equals P2V2. We are assuming temperature stays the same because that's what Boyle's law does. So you'll notice that we don't have this second volume. All we're missing is V2. So you can either solve for V2 now or plug in all your numbers and then solve for V2. I'm going to go ahead and solve for V2 now. So the first step would be divide both sides by P2. And we get this. P1V1 over P2 is equal to V2. Easy peasy. And then we do this. Now we can actually plug in our actual numbers. The first pressure we had was 210 kilopascals. First volume was 4 liters. Second volume is 2.5 liters. Oh, can't see that. 2.5 liters. So multiply those two and divide by 2.5, and what do we get? 340. Not too bad, right? The only thing you needed to remember was use Boyle's law for this because temperature is staying the same. The picture might help, kind of. Since this gets smaller, we can think of that since the volume got smaller, everything got squished, so the pressure should be higher, and that makes sense with our answer right here. Our 340 is definitely higher than our 210. So we're good on there, and that's it for example problem 14.1. I don't think 14.1 and 14.2 will give you guys much trouble. It's building up for 0.3 and 0.4. Those are the tough parts. So let's go ahead and look at this example for Charles's law, and let's switch colors because why not? We'll use blue for this. Okay. It says a gas sample at 40 degrees Celsius occupies a volume of 2.32 liters. If the temperature is raised to 75 degrees Celsius, what will the volume be, assuming the pressure remains constant? Okay, so we're heating up something, but the volume can change, but the pressure can't. Okay. So that to maybe like that. 40 degrees Celsius, and this is 75 degrees Celsius. Volume at 2.32 liters. We don't know what this volume is. And we know pressure is going to stay constant. So we're heating this up, and you might think, well, last problem, when it was squished, it was higher. It doesn't really work because we're assuming pressure remains constant. So as we're heating this up, whatever this container is made out of is able to stretch to make sure that the pressure is always the same, even if the volume is not. So we're heating something up, changing the volume, keeping the pressure the same. If you remember, though, we have to keep temperature in terms of Kelvin, not Celsius. So the first step you'll see here is to convert the temperatures from Celsius to Kelvin. And all you have to do is add 273 to both of these. So our initial temperature, instead of saying 40 degrees Celsius, we're going to say is 313 Kelvin. And instead of 75 degrees Celsius, we're just going to add 273 to that. And that gets us 348 Kelvin. That's pretty easy. I probably wrote all this stuff too big because we're not going to have room to do the other stuff unless I do this. So let's look at the actual problem. We have our T1, we have our V1. We do not have our V2, but we do have our T2. So let's go ahead and do this for Charles's law. Okay, once again, we're looking for the second volume. We're looking for V2. So let's rearrange this equation to solve for V2. The way we're going to do that is to multiply by T2 on both sides. So we multiply the T2 up here, and it becomes T2V1 over T1. Then all we need to do is plug in the numbers we actually have. It's getting a little weird, but plug in the numbers that we actually have. T2 is 348. V1 is 2.32 liters. I don't have enough room to write the units. And T1 is covered by my head, 313. So 348 times 2.32 divided by 313. And our second volume, this volume right here, is 2.58 liters. Okay? And that makes sense because this second volume is bigger than this in our picture, right? That's what we assumed in the beginning because you're heating it up so the material can stretch to expand it. Well, it did, and our math proves that. It did get bigger. Not by a lot, though. 2.32 to 2.58 liters, not a big increase, but you also have to realize that going from 40 degrees Celsius to 75 degrees Celsius also isn't that big of an increase. So not that big of an increase in temperature makes a not that big of an increase of volume, so it actually works out exactly to what we would expect for that kind of problem. So that's how Charles's law works. You guys have that blinding white light right here to deal with. It's actually just a gray shed. I don't know why it's reflecting light like that so much. I can barely see my hand. Like I'm. Let's go for green for Gay-Lussac's law. Oh, there it is. I'm going to write that over there so I can see it on my screen. All right, so Gay-Lussac's law. The pressure of a gas in a tank is 3.2 atmospheres at 22 degrees Celsius. If the temperature rises, what will be the gas pressure in the tank? Okay. Well, in this case, keeping volume exactly the same both times. So pretend those are the same boxes. As a result, once we heat one thing up, once we heat it up, the pressure will be a lot higher because all the particles in there running around, they have a lot higher kinetic energy like we talked about in chapter 13. So initially, our pressure is 3.2 atmospheres at 22 degrees Celsius. And then we don't know our second pressure, but we do know it was heated up to 60 degrees Celsius. Well, remember, just like last problem, we cannot use Celsius for this. We got to switch to, right there, it says we got to switch to Kelvin. So let's add 273 to that. It becomes I could have done that. 295 Kelvin. And let's add 273 to that. That is, yeah, 333? Yeah. 333 Kelvin. So we have the initial temperature and the final temperature, or should I say the T1 and T2. We also have P1, but we do not have P2. So let's go ahead and write our equation down here. P1 over T1 equals P2 over T2. Remember what we're looking for? We're looking for P2. Well, we're looking for P2. So solve for P2, and the way we do that is multiply both sides by T2. So now we have T2 multiplied by P1 over T1, right? Because that went up here. And that equals P2. So our second temperature was 333 Kelvin. Our initial pressure is 3.2 atm. And we divide that by our T1, which is 295 Kelvin. 295 Kelvin. So then, once we do all that, our second pressure, multiply 333 by 3.2 and then divide by 295, and we get 3.61. That makes sense because that is higher than our initial pressure, and we were heating a closed container. So you see like the warnings on stuff like don't leave this pressurized container in the sunlight for too long. This is why, because you increase the pressure on that container just by heating it up. The container can't change shape, so it's going to explode eventually. But that's Gay-Lussac's law. Now let's go ahead and go to the combined gas law. Okay. A gas at 110 kilopascals and 30 degrees Celsius fills a flexible container with an initial volume of 2 liters. The temperature is raised to 80 degrees Celsius and the pressure increased to 440 kilopascals. What's the new volume? So according to the lesson, the combined gas law is when we combine the gas laws, all three of the ones that we just did, smush them into one equation, and you can actually solve any of the problems from the previous section using this equation. The thing is, remember, for each of those gas laws, we just pretend one of either temperature, volume, or pressure is constant. So in a problem like this, that would just cancel out. In a problem using this equation, it would just cancel out. But for this specific problem, all three are changing from one set of data to the next. So since all three are changing, we need to use the combined gas law. We can't just pick one of the three laws that we learned before. So it says we're given the initial we're given the initial pressure, temperature, volume, and we have the final temperature and pressure. We need to find the last volume. Okay, so it's P1 V1 over T1 equals P2 V2 over T2. And in case you didn't catch it, you'll notice that if you take out the T1s, you have that first law we did. And it works the same way. If we take out the P1, then we have V1 over T1. That was one of the gas laws we just did. And then this is also one of the gas laws we did, P1 over T1. So it's literally just putting them all together in one spot. You'll see here that all of the given information is right there, so I'm not going to rewrite that. All the initial, the P1, T1, V1, and then the T2 and P2. And then it says on the far end over there, we don't know what our second volume is. If you don't know what our second volume is, that's the thing we're trying to find. So what we're going to do is isolate that. So the first step is to multiply everything by T2. So we get T2 P1 V1 over T1 equals P2 V2, right? We multiplied the T2 over there, so now he's hanging out with them. And we want to get rid of this P2. So now we divide everything by P2. So this goes on the bottom. And now we have T2 P1 V1 divided by P2 T1 equals V2. Okay, right now we're just doing algebra. We're just moving the variables around. Now we get to plug in all of these values into our calculator and let them do the heavy lifting, unless you want to do all this multiplication. So I see I need to put T2 in here, but I can't just put T2 in there because the temperature that it gave us was in Celsius, and we know that we can't use Celsius, we have to use Kelvin. So you'll see right here, we switch it to Kelvin, right? So 273 plus 30 gives us 303 Kelvin. So that's what that is. That's our T2. What was our first pressure? Well, looking at that chart, our first pressure was 110 kilopascals. And then what was our first volume? It was 2 liters. What was our second pressure? 440 kilopascals. Parentheses. And what was our last temperature? Remember, we have to convert it to Kelvin. So if we look right here, it says it is 353 Kelvin. All right, so let your calculator do the work. Multiply everything on the top, divided by everything on the bottom. And we get an answer that is right there, 0.58. And we know it's liters because we're talking about volume, so the answer should be in liters in this case. And that's the example of a combined gas law. Pretty straightforward, I think. Move the algebra, or use the algebra to move the variables around until you get the one you want isolated. Plug in everything, and let your calculator find the answer. Easy peasy. You have a counter how many times I've said that this lesson? I don't think so. Last up, we have an Avogadro's principle problem. Pretty easy. Avogadro's principle uses moles and that conversion factor. Calculate the volume that 0.881 moles of a gas at standard temperature and pressure, or STP, will occupy. So we learned that standard temperature and pressure means that 0 degrees Celsius at 1 atmosphere. And we also learned that it doesn't matter what gas we're talking about, a mole of a gas takes up the same amount of space and stuff at STP. And so we start with 0.881 moles of whatever gas. It doesn't actually matter. We want to know the volume it takes up. Well, if you look at the example, if you look over there, it says the number of moles of a gas should be multiplied by the conversion factor, 22.4 liters, for every mole. I'm going to use that as a conversion factor like we used to do in the previous section. So if we start out with that's an 8. We start out with 0.881 moles, and I want to get volume as an answer. I can use this conversion factor because I know it's 22.4 liters for every 1 mole. So if moles up here, I want to cancel out moles on the bottom and put the 22.4 liters on the top. That way our unit is going to be liters. 0.881 times 22.4 is 19.7. That's it. That's the easy mode version. Now let's do the slightly more complicated version. Calculate the volume that 2 kilograms of methane gas will occupy at STP. Okay, now it's giving us a mass, and now it's telling us what type of gas it is. The reason why it's doing that is because we're going to have to go from how much mass that is to how many moles that is to the volume of that. So we're going to go through a couple steps in order to get there. So you can follow that if you want, but let's go ahead and go from mass to moles. My voice just cracked. Mass to moles, and then from moles to liters. Okay? So first up, we have 2 kilograms of methane. I want to convert that to let's write this a little smaller. So I want to go from mass to mole. The problem is if I use molar mass, like all of you should be saying right now, if I use molar mass is in grams, not kilograms. So first, let's convert this to grams. And the way we do that, well, for every 1 kilogram of methane, how many grams is that? 1,000. Now we want to go from grams of methane to moles of methane. And the way we relate moles and mass together is the molar mass. So you'll see what they do right here. They calculate the molar mass. There's 1 carbon atom and 4 hydrogen atoms, which gives us a total molar mass of 16.05 grams per mole, because there's 1 carbon and 4 hydrogens. So that means there's 16.05 grams for every 1 mole. Okay, so we've gone from mass to moles at this point, but now we want to go from moles to liters. Well, now we're going to use that universal conversion factor at STP. For every 1 mole of a gas, there's how many liters? 22.4. Okay, so I do it all in one step. You'll see the book does it step by step and does it in like separate things. To me, that's just confusing. I like this all in one step because kilograms of that cancels out, grams of that cancels out, grams cancels right there, moles cancel right there. We're only left with liters. So 2 times 1,000 times 22.4 divided by 16.05. And that gets us 2.8 times 10 to the 3rd liters. And there we go. And that is it for the example problems for 14.1 and 14.2.